everyone. It's an honor and pleasure to be here and speak to you. Thank you for the introduction. Thank you for the invitation. What I would like to tell you about today are problems in combinatorics that require, say, more artism than craft. So we'll have a look at problems about tilings and colorings of rectangular boards, which is a common topic in both national and international Olympiads. And we'll see the intuition behind these astonishing solutions, very colorful. And I'd like to not only show you the problems and possible ways of thinking, but also like I said, the intuition behind and how to come up with those artistic, colorful colorings. And the first part of our meeting, this presentation of mine, is going to be divided into just problems that are training problems or problems that have appeared in competitions before. And I would like to to deliver the intuitions via these problems, this couple of problems prepared. Okay, so let's start. You cannot start this topic from another problem. It's a classic one. It's called the Mutilated Chessboard problem, and it reads as follows. Can an 8x8 board with two opposite corner cells removed, you can see we don't have them, be tiled with dominoes? And before we proceed to thinking of the problem, let me be precise. What do I mean by tiled with? It's intuitive, but for the sake of completeness, let's just say it. To tile something with some other figures, we mean that there are no overlaps. Okay, so we cannot put two dominoes, for example, like this, as they would have a common cell, right? We have no sticking out of the board. So, for example, you cannot place a domino like this or this. And the other natural condition is that they should contain whole cells. Yes, so we want to place them on top of two squares and not, I don't know, like this or like that. And the problem asks whether it's possible to divide those 62 cells into 31 dominoes, so figures as presented to the left. And well, what can you do to start solving such a problem? You can try, right, to put some pieces around and see if you can make it to cover everything, but it would turn out, I won't do it anymore, that is hard, maybe impossible. But how to prove it's impossible? First thing, we can count the cells. Like I said, there are 62 of them. So 62 is the number of all the cells. Yeah, but it's an even number. There is no obstacle here for 31 dominoes to cover it. Yet, it is impossible, and the argument is a bit more sophisticated. And here is what it is. The idea here to prove that it's impossible to cover is to color everything like a chessboard, so alternately black and white, and see what happens, how this chessboard interacts with our problem, the conditions. So after we color in a chessboard manner, we can observe that each domino placed anywhere, horizontally or vertically, will always contain one white and one shaded square, right? So in particular, if it was possible to cover everything with dominoes, then the number of used dominoes should be the number of shaded squares in the picture. Yeah, but after you count them, it turns out that the number of shaded squares is only, I guess, 30, right? And the numbers of dominoes you need is 31. these are not equal. And voila, that's it. That's the reason why there is no such tiling. Another way to phrase it would be to observe that we have, as I said, 30 dark cells and 32 white squares, right? Because no white square got removed. And those are not equal. Whereas every domino would contain precisely one black and one white, right? So our tiles are balanced in a way that they cover the same amount of black and white area, and our entire polygon is not balanced because it has different amounts of black and white cells. So those are the two reasonings. But what you may consider not satisfactory is this rabbit out of a hat, yeah? Let's take a chessboard. It's like a trick, and it came out of nowhere, right? And we don't like to solve problems, Olympic problems like this. So let me encourage you let me tell you that it's actually not that tricky and not that unnatural, because we can derive this coloring and see that it's actually gonna work here. We need to change the way of thinking though. Instead of having a ready trick, let us have an idea to try to color everything in a way that every tile would cover two different colors, right? We have dominoes which consist of two tiles. So let's take two colors and let's try to color it in a way that every tile would consist of different colors. So for example, if we color this cell red, right, then given that we can have a domino placed like this, like this, like this, or like this, we should have those four cells colored blue. And continuing this reasoning, we could have a domino placed like this or like that, or like this even. So the remaining cells around should be red again. And you can extend this coloring in order to obtain nothing but the chessboard. So look what happened here. We took a tile that was given in our problem, and we used it to extract the proper coloring of a board. That would come in handy. Yeah, and just as before, we can now count number of cells of each color. We have 32 blue and 30 red, and it contradicts the fact that every domino contains exactly one red and exactly one blue. Okay. So you may get the feeling that you just saw 3 times the very same reasoning, but let me tell you that you actually didn't. Yeah? That there were slight, subtle differences, which will turn out to be important in later examples. Okay. So before we proceed to different colorings, different problems, let me try to defend this chessboard as a generic trick for a problem, because it turns out that simply putting a chessboard coloring inside might be the only thing you need to do in a problem. Putting like from nowhere, from a hat, yeah, right. So let's have a look at this problem, problem B. It asks whether a board 10 by 10 can be tiled with T tetrominoes. What is a T tetromino? You can see it in the left margin. Is a tile consisting of 4 cells in a shape of a letter T, and any tile that is rotated with respect to this one. So we can have also those orientations. Okay, so we are asking whether we can tile this board with T tetrominoes. Well, it's a reasonable question, right? We have 100 cells. Each T tetromino consists of 4 cells. So technically, it would be possible to tile it with 25 T tetrominoes. But again, after we try to tile it, it seems like it's very hard or impossible. You can go, for example, tile a 4 by 4 square like this, but let's try to prove that you cannot tile 10 by 10 square. And here the way would be to just take one of the colorings that come to your mind, right? For example, chessboard coloring, because we just solved the problem about it, and see how our tiles will behave with respect to such a coloring. Okay, so use a known coloring and see how our tiles behave. Okay, so let's have a chessboard and let's try to place tiles on our chessboard, our T-shaped tiles. And what we can see is that every tile has one of two options for behaving with respect to coloring. It either contains 3 white cells and 1 shaded cell, or it contains 3 shaded cells, right, and 1 white cell. Having observed this, we may have a look at numbers of tiles of each kind. Yeah, so for example, let's have a look of numbers of number of tiles dominated by white color and number of tiles dominated by black color, and see if we can, I don't know, write an equation or compare them to something. So for instance, we know that the total number of such tiles, if we had a tiling of our 10 by 10 chessboard, should be 25, right? Because we have 100 cells to be covered. Yeah, but on the other hand, we can distinguish the two tiles by the numbers of shaded cells contained inside. So for example, we can count number of shaded cells, which is 50, right? Because exactly half of them are shaded. Count with respect to what tile do they belong to. Yeah, so suppose we have some tiling of these, and we are counting shaded cells. Yeah, so each shaded cells contained in each such red one contains 1 shaded cell. Okay, so for each such tile we get only 1 shaded cell, whereas each such tile, the blue one, will contain 3 shaded cells. Okay, so the total number of cells within the entire board is 1 times this number of these guys plus 3 times number of these guys. And given that we know that this plus this is 25, we get that it's 25 plus 2 times number of the black ones dominated by black. And you can see a contradiction now, right? Because we would need to have twice the number of tiles of this kind, the blue ones, be equal to 25, which cannot hold, right? Because 25 is an odd number and twice a number of tiles is an even number. So what I would like to show you with this problem is that coloring is not everything you should do, right? After you color and observe, you can do some counting, you can provide some parity arguments or arguments modulo some other numbers than 2, and arrive at the contradiction with the assumption that such a tiling existed. And sometimes chessboard is just enough for such a reasoning. You may try to think about different sizes of chessboards here, when they can be tiles with T, Chetrominovs, and were not. And you can try think of trying to develop another coloring that will solve the problem. I encourage you to try whether you can find another solution. Right, but chessboard is not everything in the world, right? So let us have a look at the following problem. Let's again have an 8 by 8 board. And now we want it to be covered with 1 times 3 tiles. So not regular dominoes, but like longer ones, say. Yeah, but 8 times 8 is not divisible by 3, so we would need another unit square to compensate that. Yeah, so we would need 21 1 times 3 plus 1 unit square. Okay, we're interested in such tilings, and let's ask if we can do it, and if so, where the unit square can be. So first attempt to solve such a problem would be to try to like fill it with 1 by 3 tiles. And for example, if you do it like this, you fail, right? Because we cannot put another 1 by 3 here and one by 1 tile. So maybe we should try differently. Yeah, but it's not that obvious how to try, right? We may try to arrange them in some clever different ways. But in order to check all possible options, we would need, I don't know, all computers of the universe, and they are not enough. And they are not available for us. So let's try to understand where the unit square could be, if it's possible to tile it like this. And in order to do so, let us mimic the reasoning from the chessboard, right? Let's not like look among all the colorings that we know, but let's examine the tiles that we have. Yeah, so the 1 times 3 tiles, those are the non-trivial ones, and try to provide a coloring that would behave nicely with those tiles. So the idea would be to use now 3 colors, because our 1 by 3 tile has 3 cells, and try to make the coloring in a way that each such tile, regardless of where it's placed, would cover 1 cell of each color. So we can try start, for example, with this place, with this potential tile, and color, say, this cell red, this green, and this blue. And now we can see that if we want this property, right, that each 1 by 3 tile covers 1 of each color, then yeah, for the case of this tile, we need this cell to be red. And proceeding, we will need this cell to be green, blue, red, etc. So we've completed 1 column. So what to do next? Well, actually, we can, for example, try to color this cell. We know we cannot color it with red because here is a potential tile that would have 2 reds inside. So it's either green or blue, basically, this cell. So let us consider those cases separately, where it's green and where it's blue. I'm trying to reproduce what we had. And I claim that now we are able to finish both of the colorings. Yeah, first of all, look at the first row. It can be filled just similarly as we did with the first column. Yeah, so the 3 colors should appear in a periodic fashion, like with a period 3, because we could assemble the tiles consecutively like this. But there is a nice observation to be made, for example, here. If you have a look at this cell, and you want this property that every potential 1 by 3 covers exactly 1 cell of each color, then you will see that this one has already a blue cell, this one has already a green one, so there is no other option. We should have red here. And similarly, you can have red here, and if you proceed with looking for the tiles, you will get something which behaves like a diagonal coloring in 3 colors. Something very nice. And let me remark it one more time. It's something we obtained just from the shape of the tile, not from some secret knowledge. And if we do a similar thing in the right example, for example, with this cell, it cannot be neither blue nor green, it should be red. So this is green and then blue and stuff again. Then you will see that we get a diagonal coloring in the other direction. So those are the 2 colorings that we obtained. And they have the property that each tile, 1 by 3, covers exactly 1 cell of each color. So what can we do now? Let's count cells of particular colors and see what are the numbers, right? So if you count it here, I won't do it like explicitly now, not to waste our time. But you'll see that there are 22 green squares, 21 red, and 21 blue. And what can we deduce from this? Well, if we were able to place 21 1x3 tiles on this board, right? Then we would have 21 covered red, 21 covered green, 21 covered blue cells. So the extra cell, the one uncovered by this 1x3 tiles, it has to be green, right? We know that it has to be green. And if you perform a similar reasoning on the right picture, then what you observe is that here, I guess, red color appears more often than the two remaining ones. And so if we are able to place a single a single square apart from 21 1x3 tiles here, then it should cover a red square on the picture, on the right picture. Okay, so what those colorings are actually saying to us is that you cannot, for example, have this cell covered by 1x1 square, right? Because after you subtract one blue, the numbers won't match. You won't be able to assemble 1x3 pieces in other place. And similarly, if we use a red square for a unit square piece. So the green ones on the left picture are the only potential ones to be the ones with unit square placed on it, if we had any tile satisfying our conditions. It doesn't prove that all of them are possible, right? But it proves that all other are impossible. You cannot place a single tile on non-green square on the left picture, and you cannot place a single unit square tile on the red square to the right picture. So now that we have two pictures, let's combine them into one. Yeah, first of all, let's note that green and red are the only colors important on the respective pictures, right? You can see here that every tile, regardless of how it's placed, would cover exactly one green cell. Every tile placed here would cover exactly one red square. There are 22 tiles on the left, 22 color cells on the left, 22 color cells on the right. Yeah, so our 1x1 square should be colored both here and here. And if it's both here and here, it must be one of the four places. So we narrowed down the set of potential places when the 1x1 tile may be placed to those four cells. And it's actually one case, because after you rotate the entire picture with any of those covered by 1x1 squared, then you will get placement for any other of those. But this is not the end of the problem, right? We didn't prove that the four cells are good. What we need to do, and please don't forget about it, because that's the place where on Olympiads you probably most often get points off in coloring problems, is to show that there are possible placement of tiles for which this is covered by unit square, right? Because maybe for a reason of some other crazy coloring, those are also bad for us, just as were the red ones and green ones on previous pictures. Yeah, but now that we know which tile should be covered by a single piece, we can assemble the. I hope we can assemble 1/3 pieces properly. And with this picture, we are done. We proved that any white square of either of those pictures is not good for us because it would make the sets of respective colors not balanced, and that 1/3 tiles are balanced. And we proved that every square which is colored in both of the two pictures, so any of these four, is good. There exists a tiling with this one tile by one square. And if we want to formulate our argument in a short and, I don't know, maybe an elegant way, we may encode this adding of the two pictures with numbers. So suppose the green cells here are ones and the red cells here are ones and there are zeros everywhere else. If we add two pictures to one another, then we receive a picture like this. And now the argument is that every 1/3 tile covers the sum of exactly 2, cover the cells of sum exactly 2, and the sum of all the cells is, I guess it's 44, right? Because we have 9 times 4 plus 8. And we can argue that each 1/3 tile covers a sum of 2. So 21 1/3 tiles would cover a sum of 42. So the unit square is left with sum 2, right? 44 minus 42. And there are only 4 possible placements, so that it has itself the one cell, the sum of numbers too. And I wanted to show you this picture because that's the picture that sometimes appear like the ultimate solution of this problem in some books, and full stop, no more comments. In particular, no comments on how to obtain this numbering. Where does it come from? Yeah, it may come from different places. Like it may as well could have come from directly from your head. Yeah, because you have the brilliant ideas of numbering tiles. But what's my point? That this is actually justifiable by all the reasonings or the heuristics we did before, and not just to be invented. Right. So, and that's like a valid remark concerning maybe not many, but at least some of the materials that you may encounter on the internet. That sometimes the solution may seem completely unjustifiable, that you have to be a genius in order to see it, but sometimes they have this like second the reasons they come from. Okay, so that was this problem. Let's switch to the next one. Maybe I must admit I have seen the comment, the one that appeared. Maybe I didn't make it clear in the very beginning. Every time it's good to make it clear. This is aimed as a introduction to coloring. So I'm sorry if among you there are people who already know the stuff like this. I will have extra problems for you, which are much more harder than the ones presented here, if you wanted, after this session. But my aim here is to like present to you the classical reasonings that go behind the tiling and coloring problems. But before the set of extra problems, let's have a look at this problem D. And it's of a bit different type than the three I've shown you before. Namely, suppose that we have a rectangle which is tiled with altered terminals and ested terminals. Okay, so for example, it could look like this. Right, it's a rectangle, and each piece is of shape of an L or an S. And what we want to prove that regardless of how it's assembled, how the tiles are assembled, we always have an even number of such L tetrominoes. Okay, now we may think how to get this evenness, where to get it from, especially given that it's regardless of the rectangle that is here. And the answer is, look, we have two tiles here, right? L tetrominoes and S tetrominoes. And we claim something about tiles of one of the two kinds, okay, about the parity of L tetrominoes. So maybe a good reasoning would be to try to distinguish the two tiles via some coloring, right? And develop a parity condition. I mean, the distinguishing should involve parity somehow. So, for example, if we try to color the grid in a way that all S tetrominoes cover, I don't know, even number of shaded cells, and all L tetrominoes cover an odd number of shaded cells, right? Then they can be distinguished by this coloring. Which I mean, if we know that our rectangle has, for example, even number of shaded cells, and every S tetromino has an even number of shaded cells, and every L tetromino has an odd number of shaded cells, then we instantly get that the number of L tetrominoes is even. Right, because this odd number of shaded cells should be counted an even number of times in order to get an even sum. Okay, so let's proceed along this line of along this idea. So let us try to color our grid in such a way that if we have an L tetromino and S tetromino, they would cover different parities of shaded cells. So for example, if we place the two like this, and possible red placement of L and possible green placement of S, then we see if we want those two tiles to be distinguished, we need to have different color here and here. Right? We need to have different colors here and here because that's the only cell that differs. And so in our coloring, the two should be of different color. And you can argue like this for any pair of two diagonally adjacent squares in order to extend it to the following observation. If we want our coloring to distinguish between R's and S's, then all the black cells should have different colors than all the blue cells. Assembled like this. Yeah, and now, having said that, we need to just pick a color for any of the remaining white cells, and everything becomes clear. So, for example, if we take black here, then we want to have even number of blacks, for example, in this S or in this S or in this S, right? So in this S, in order to have an even number of black squares, we need to have this blue. And in the two remaining ones that I showed you before, we need to have it black. And what we get is this zebra pattern coloring in stripes. We we examine carefully. And again, this is the coloring that came only from the tile shapes and not from we don't know where. After we color it like this, we can see that every L placed in any possible position covers an odd number of black squares, and every S covers an even number, precisely 2 of black squares. So to finish our problem, it remains to claim that we can place this rectangle on this colored grid in a way that it contains an even number of black cells. Because if a rectangle has an even number of shaded squares, and each S-tetromino has an even number of shaded cells, and each L-tetromino has an odd number of shaded cells, then it follows that the number of L-tetrominos is even. Yeah, but this last step is somewhat. You need to be careful here. But if we have a rectangle which is tiled with those tiles, right? We have L-tetrominos and S-tetrominos, and each of those has 4 cells precisely. So our entire rectangle has a number of cells divisible by 4. And if it's divisible by 4, the area of the rectangle and its side lengths are integers, then we are sure that at least one side length of our rectangle is an even integer. And if it's an even integer, we can place our rectangle, for example, like this, to have the, oopsie, this is not even, to have the even sized side parallel to the zebra, right? And now we are sure that the number of shaded cells inside is an even number, because it's a multiple of this 2m, which is the side of this rectangle. Yeah, the reasoning that I delivered beforehand was supposed to be in this white space. Okay, so to sum up, yeah, not only counting of colors of cells of particular colors is helpful and important. Also, this parity counting, so counting modulo 2, can make the conclusions follow, the desired conclusions to follow. So let's change the flavor a little bit now. Let's introduce some general parameter in order to resemble an Olympic problem a bit more, supposedly. The problem is like this. Let's call a tile, which is a rectangular tile, an even rectangle if both its side lengths are even numbers. So, for example, in the picture below, we have 2 by 4, 2 by 2, 4 by 4. The green rectangles are even rectangles because both side lengths are even. And now let's have a look at the following problem. Given an n by n board where n is odd, right? So, for example, here n equals 7. We want to tile it with even rectangles. Of course, we won't succeed because even rectangles have even areas, for example, and they won't cover the entire square. So we want to use also unit squares, yeah, the yellow ones. But we want to have even rectangles covering as large area as possible. So we want to use as small number of unit squares as possible. And the question is to determine the smallest number of used unit squares in such a tiling. Of course, in terms of n. So note that if we had an even sized board, then the problem would be trivial, right? Because we could have just one big even square and that's it. No 1 by 1 tiles. But now it's a bit more interesting, arguably. And again, you can try to derive some general examples which have as small as possible number of yellow tiles, but they're not a proof that you cannot have less. Maybe there is some fancy tiling that no one will come up with, right? It's like very chaotic, but minimizing the number of unit squares. So now it turns out that colorings may help you with these optimization problems as well. You can bound the number of tiles using coloring, and we'll see in a moment how. But let us first remark that it's always possible to place a large even square in a corner of our odd square, right, and fill the remaining L-shaped figure with units, with unit cells, with unit squares. And that way we would have, if this is n, right, and this is another n minus 1, and we can always provide the tiling with exactly 2n minus 1 unit squares. And it turns out that it's indeed the optimum. So it's not like there is a crazy tiling that is optimal. This very simple one turns out to be optimal as well. But let us see why is it the case. And the first step to make here would be to note the following observation, that even rectangles having both of its side lengths even are precisely those rectangles that can be subdivided into 2 by 2 squares. Right. And on the other hand, each 2 by 2 square is an even rectangle, right? So if you tile with 2 by 2 squares and 1 by 1 squares, then it's a tiling with even rectangles and 1 by 1 squares. So this shows that these two problems are in fact equivalent, and subdividing each even rectangle to small 2 by 2 cells makes it, I guess, simpler to think of, and we get another shape of a tile which we can work with. And so let's restate the problem in an equivalent way. We have n by n board where n is odd, and now it's tiled with 2 by 2 tiles, right? Even rectangles, but the small even rectangles, and unit squares, just as before. Now, in order here to minimize the number of unit squares used, here it's equivalent to maximize the number of used 2 by 2 tiles. And in order to have as small as possible number of yellow squares, it's enough to have as large green area as it's possible. So our problem boils down to estimating the total number of 2 by 2 tiles from above. What is the maximum number of 2 by 2 tiles used in a covering of an odd side length square? Well, and now we know what to do, right? Because we have this tail shape now. So let's try to derive a coloring which matches this shape. Okay, so for example, again, let's have each 2 by 2 square, regardless of its placement. Let it cover. Let's try to design a coloring where it covers one cell of each color. Okay, so for example, we can have this square red, this one yellow, this one green, and this one blue. Yeah, and that our 2 by 2 square allows us to just repeat this pattern periodically, right? With period 2 in both directions. So in order to have, for example, this piece covered by covering blue, green, red, and yellow, it's enough to have this coloring shifted here. So what we get is a picture like this, and analogously we can shift horizontally. Maybe let me not draw. Let me just show you what we obtained. And this is a for coloring of this square, but it can be extended to the coloring of the entire plane with the nice property that every 2 by 2 square has 4 cells or 4 windows of pairwise different colors. So when we restrict side to only one color, for each of these colors, we know that our 2 by 2 square will contain exactly one cell of our favorite color. So for example, in this picture, it tells us that we cannot have more 2 by 2 squares than we have cells of our favorite color. Okay, so for example, we cannot have more than 16 2 by 2 squares because we have 16 yellow squares. We cannot have more than 12 2 by 2 squares because we have 12 blue squares. And finally, because our favorite color is green today, we cannot have more than 9 2 by 2 squares, right? Because we have only 9 green cells here. And every 2 by 2 square will cover exactly one of those. So number of 2 by 2 squares less or equal than 9. Or in general, if this is n, then this is n minus 1, and this is the green ones are precisely every second. So n minus 1/2 would give the number of 2 by 2 squares. It is at most n minus 1/2 squared. And it gives us the desired result that the smallest possible number of 1 by 1 squared is 2n minus 1. And because as you see here, that's precisely the example that we had before. And so to be maybe a bit more precise, number of cells covered by this 2 by 2 tiles is at most 4 times the above number, which is n minus 1 squared. So the number of 1 by 1 cells is at least the number of all cells and squared minus the number of cells used in even squares, which is n minus 1 squared is precisely to n minus 1 in general. So this is another advantage of having colorings, controlling our tiles in some way. Here, controlling by means of this equality of number of shaded cells inside each possible tile, right? That it can give us the conclusion that the number of tiles is bounded by the number of cells of this color. Okay. So having said all of this, and those intuitions might be a bit too much intuition behind the stuff. Let me show you one problem that I consider very, very beautiful and not that straightforward, actually. It appeared in some local European international competition. The problem is as follows. We're given a 7 by 7 board, so not a large one. And it is to be covered with one-sided p pentominoes what do I mean by one-sided? I mean that this is not a p-pentomino, right? This is wrong. We cannot we cannot flip the tiles to the other side. It should be a p, not a q. And so we have a collection of p pentominos, and we have a 7 by 7 square, so we have 49 cells. So it would be, and what we want to do is to have 10 such p pentominos to cover 50 cells of this grid. And the reasonable expectation is to have exactly one cell covered by 2 tiles. Okay, so exactly one cell is to be covered by 2 tiles, and all the remaining ones with exactly 1 tile. And it, like the numbers match. Okay, we have 50 cells here, 49 here, but we allow 1 cell here to be covered twice. And the question is, which of those tiles can be covered with 2 p's? Right, so it's a bit another way around that in two problems before, where we had this 1 by 3 and we wanted to cover everything but for 1 square. Now we want to cover 1 square twice. Okay. So what can we do? We can try to cover and see if we can find a covering for particular cells, but we still need to prove that all the other ones, the ones that we cannot find a proper tiling with, are bad, right? That you cannot find a tiling with them covered twice. So the first idea is somewhat following from all previous ideas, right? Let us color it in a way that each p pentomino covers 5 different colors, as it has 5 different cells. Okay, so for example, suppose this is our p pentomino somewhere here. Let it have colors like this, right? You can see that it's a possible placement of a p pentomino. And what are other possible placements? For example, this is a possible placement, which means that if we want to have this coloring work as we want, we need to have this cell red. Right. Oops. Red. And very similarly, this is a possible placement of a p pentomino, so we want this cell to be red as well, and this one, and so on. Right, because we can always make such windmills with our p pentominos overlapping along 2 by 2 squares. And if we perform such operations consequently, then we get a coloring that looks like this. Now you can count tiles of each kind, or just see from the picture that the green color is special, right? It's symmetric and nice. That all colors apart from green appear on precisely 10 cells, and green appears on precisely 9 cells. So what's the reasoning now? The reasoning is as follows. If we have 10 p pentominos and only 9 green cells, then the cell covered twice should be green, right? And actually the other colors don't matter. So we have, let me say it one more time, we have 9 p pentominos, we had 10 p pentominos and 9 green cells. So so the one covered twice should be one of those. So this is nothing new compared with the reasoning from previous problems. Yeah, but it turns out that not all of them are good, right? This is one coloring that we use, but for most actually of the green cells here, you cannot find the proper tiling covering those cells twice. Yeah, and in order to come up with a reason or come up with another coloring that resolves the problem to the very end, we can stare a little bit longer at our argument here with 9 cells. So look, we have exactly 9 green cells, exactly 10 deep and dominoes, and it follows that doubly covered is green. And one important thing, each deep and domino covers exactly 1 green. Actually, what we need here is not exactly 1. We only need each P to cover at least 1 green cell. This makes our argument like even stronger somehow. Yeah, so suppose we have 9 green cells, 10 P pentominoes, and we want that each P pentominoes covers at least 1 green cell. So then 10 would cover at least 10 green squares, right? So the one covered twice should be green as well. And we have extra conclusion that no P pentomino in the proper tiling should cover more than 1 green, right? If there was a possibility for a P pentomino to cover more than 1. Yeah, but actually we can come up with another collection of 9 special cells with the property that each P covers at least 1 of them. And in order to come up with it, we can either remember the picture from the last problem, or try to, or see that a P pentomino, for example, contains this 2x2 square as a subtile. So maybe it's reasonable to consider coloring for this 2x2 square. And we can draw a picture like this, in which, let me tell it one more time, each P covers now at least 1 shaded, right? At least 1 shaded cell, but it can cover 2. And the reason why it covers at least 1 is that it contains this 2x2 square, which covers exactly 1. Okay. So applying our reasoning, the one with inequality, to the right picture, we get that the doubly covered cell should be red on the right picture, right? And because 10 P pentominoes would cover at least now 10 red squares, so the one covered twice should be red. So let's merge pictures and see that only the central tile is shaded in both of them. So it's the only remaining candidate for the solution. Yeah, and in order to finish the solution, it's enough to draw a tiling with piece that covers this cell exactly twice. For example, like this. Okay, we're running out of time, but I really want to show you the last problem I prepared for you for today, which is a problem that comes from IMO shortlist, and it comes from IMO shortlist, a recent IMO shortlist with number C4, I guess. So it's not the easiest combinatorial problems, at least according to the problem selection committee. And it turns out that having the intuitions and knowledge that we gained today, we're able to solve this problem. And the problem reads as follows. Now we have S and Z tetrominoes. Now they differ, so we are not allowed to flip them over to the other side, right? So S and Z are different shapes. And we suppose that some figure or some polygon can be tiled with S tetrominoes only. Okay, so that we can tile something only with S tetrominoes. Let me try to show an example. This is maybe a small example, but a valid one. Right. Only with S tetrominoes. And what we want to prove is that no matter how we tile this polygon with S and Z tetrominoes, we will always be able, we will always use an even number of Z tetrominoes. Okay, so the parity is fixed of one of the two tiles that we are that are at our disposal. So, for example, this region can be tiled in a different way, using Z, for example, like this. Just toggle this this small gadget, and then we see that they're exactly 2. And what we want to prove is that regardless of the shape and regardless of the tiling, if it's possible to cover with S's only, then it's covered to, then every covering contains even number of Z's. So what should we do in order to solve such a problem? We should try to develop a coloring, right? Design a coloring which distinguishes these tiles from these tiles parity-wise, right? So let's shade some cells in order for each S tetromino to cover even number of them, and each Z tetromino to cover an odd number of them, of shaded cells. Yeah. And then if we know that F is covered using only S tetrominoes here, only S tetrominoes, we know that the total number of shaded cells within F is even, right? Because each S has even number of shaded cells. So after reassembling the tiles and changing some S's to Z's, we know that we have still even number of shaded cells covered. So we need an even number of Z's, as each Z covers an odd number of cells. But no, we need to find such a coloring. Okay, so let's have a potential Z placement and a potential S placement. And what we can see is that the two cells should differ in color, right? If we have an odd number of shaded cells here, and we want to have even number of shaded cells here, we need the two to have different colors. It's one observation. And another observation would be that, look, if we color a 2x2 square somehow, I don't care, for example, like this for now, then we are able to extend this coloring of only 4 cells to the entire plane, right? Because we have this, 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 and the parity is all the time is induced. So we can extend and extend and obtain a proper coloring. Obtain some coloring and then verify that it's proper. So we have only 16 choices to start with, right? 16 colorings of the 2x2 square, and try to, for example, draw all of them in black. So we want each S tetromino to contain, for example, like this, like this, like this, to contain even number, so that the 4 are black now. This can be deduced to be of the other color, and if we proceed, I'm rushing up a little bit, as you can see. then what follows is this nice coloring, which actually solves the entire problem because it can be verified to indeed have this distinguishing property for S tetrominoes and Z tetrominoes. So regardless of the way we place S tetromino, it always covers even number of shaded cells, and regardless of the way we place Z tetromino, it always covers an odd number of shaded cells. Okay, so this is IMO shortlist problem, and this is a link that will be copy pasted to the description of this recording and available to you as well, under which you find a lot more, like 4 times more, I guess, problems that you can try to solve on your own. For example, applying the intuitions that you got today. In case you wanted any hints to them, you can email me. There is my email contained there as well. And this is all of the stuff I prepared for you. I hope at least a little bit of those, and thank you. Oh, I think we cannot hear you.
Sorry. Thank you very much for the insight that you shared into the questions today. It was really insightful and very helpful, I'm sure. Everybody agrees with me. Now we'll move on to the questions and answers session. First, I would like the audience, if anybody has any question, please ask them.
I had one question in problem number E, sir. Can you explain this step after that n minus 1 by 2 whole square? Yeah.
Okay, I may have rushed here a little bit. Okay, so we are here, and we know that every 2 by 2 tile, right, it contains exactly 1 green cell. So the number of green cells, we can count it to be n minus 1 over 2 squared, and now the reasoning is as follows. Knowing that each 2 by 2 contains exactly 1 green, right? We know that the number of 2 by 2s placed on the board cannot be larger than this, because they don't overlap according to our tiling criteria. So this is the maximum, at least this is a bound for a maximum number of 2 by 2 squares to be placed on this board. And this, basically by some algebra, this rewrites as a smallest possible number of 1 by 1 tiles, this unit square tiles in such a covering, right? Because if we count all the cells in all such tiles, each such tile contains exactly 4 such cells, right? Because it's 2 by 2. Then we get 4 times the number of tiles, which is n minus 1 squared. So we know that there are at most this many cells, unit cells, contained in the 2 by 2 tiles, which means that all the remaining cells must be contained in 1 by 1 tiles. And there are at least this many of them, because those are all the remaining. These are cells contained in 2 by 2s, and this is the number of all cells in the picture.
I didn't understand how 4 times n minus 1 whole square is there instead of 4 times n minus 1 by 2 whole square.
I mean, the multiplication by 4 comes from this number. This is not the number of tiles, but it's the number of cells contained in tiles, right?
Yes.
Yeah, so after we calculate the square, we'll get n minus 1 squared over 4 times 4 maybe let me rewrite it here. Yeah, this equal to n-1 squared.
Yeah. I got confused there.
Yeah, so
Yes.
this is the notation bug. Say. Yes, I hope
Okay,
it's
sir.
clear now.
I didn't see that equal to sign, so I got confused a little. Thank you, sir.
Thank you. Thank you for the question.
If anybody else has any questions, please.
Oh, and I also had one question, like in the last problem and also in problem number F, I think we did something, we did coloring, but like there is something, but we like for the P pen to minus, didn't we do like didn't we have some overlapping thing also, like overlapping kind of P pen to minus?
Yeah, that's right. This is not the standard covering with non-overlappings, as we allow in the problem statement exactly one overlapping, but it's like no overlapping rules apply to the problem, but for this potentially one special place when we have to possibly two tiles.
Oh, okay. Thanks.
But we trace this overlapping in the reasoning, saying that we have like 9 green squares and 10 tiles. So the overlapping, the one and only overlapping, should happen on one of those 9 squares.
Okay, sir. Yes, sir.
Thank you.
More question, guys. If you have any, please ask. I guess
questions, you can give feedback and let me know what to improve.
it was a really interesting session. Yeah. So
I think like if we I think one of them I got confused in the middle because like for me like commutative is a hard subject, and like I kind of felt like we were moving a little bit fast because like in Nepal we don't have any like prior trainings, so like we are basically like only know about permutations and combinations, which we are also taught by so like it kind of felt a little hard, but like the session was very wonderful. But I think most will agree with me, like a little bit, only a little bit, like little bit, I don't know what that term is, but a little bit fast forward or something like that. So yeah, that's only my thing. But the like the problems and the like the strategies used for like taking out the possible taking out the like maximum number of possibilities were great. So yeah, just that if we had if we had a little bit more time, then we could have moved more slowly, and we could have I could have understand more. So that is only my like final thing. But the session was wonderful, and like the strategies especially. Thanks. That's all.
Thanks for this comment, and for the entire remark. I guess if there are more of you who found it a little bit too fast, I admit it. I wanted to show you lots of nice stuff, and 1 hour is not so long. But I do offer contact with me via an email, and the problems that a link to whose is available here. Oh, it's not clickable, but I can show it. The problems are, they look like this. The problems that we discussed today are marked within the set. That's the reason that they are letters, not numbers, because they don't appear consecutively in this problem list. And in case any of the problems that were presented is not clear, I hope after rewatching the video, for example, with pausing a little bit, it should be like understandable. And if you have some problems with the remaining exercises, then there is this this email of mine inside here. and I will try to help you with understanding it better if you wanted to train your skills in direction of these problems. So I hope it might be helpful in case the pace was too fast.
Thank you, sir. Yep. So yeah, I will contact you.
Thank you very much. There were also some questions in the form, not specifically on the topic that you discussed today. I'm putting one in the chat. Sum of binomial coefficient at even position and odd position are the same. I have seen a proof of it, but it was way too difficult for me to comprehend. Could you give a visual proof or a simpler proof?
Okay. Okay, so I guess this is true only if n is at least 2, I guess, right? Or maybe at least 1. Okay, so some boundary cases. So in general, I think the equality the problem is about is that why is this etc. Right? Why is this equal to that? Am I right? Is this what the problem is about? How to visualize this equality? Okay, so I'm not sure what is the difficult proof, but the way I see this equality always is the way is the following way. What does the left-hand side mean? It means that the number of odd-sized subsets of an element and an element set, and this is this number of odd-sized subsets, and this is nothing but number of all even-sized subsets of the set of n elements. Yeah, so for example, taking, I don't know, n equal to 4, because I have 4 colors, we have this odd-sized subsets. I'm trying to be visual. So for example, we have 8 such subsets, and here we have even size subsets. So there is one empty set, right? We have oops. Let me try to draw it nicer. We have 6 such pairs, and we have a complete set of all colors, right, of size 4. And the way I encourage you to see it is that we can find a bijection, so matching between elements from the left-hand side with elements of right-hand side. For example, choose your favorite color, let it be green, right? And if we have a set, then if it contains green, remove it, and if it doesn't contain green, add it. Okay, so the sets join in pairs. For example, this set without green will match with this set with green, added, right? This set with green will match with this set without green. This set with green will match with this set without green. This set with green which will match with the empty set, right? After we remove green, there is nothing more at all. And so on. I don't want to draw more arrows because it would make it not visible. But what you can observe is that we always have one set on the left side and one on the right side. And the reason is that if you add or remove just one element, you change the parity, right? If you had an odd-sized set, then you get an even-sized set. after removal or addition of one element. And if you had an, say, even size set, you remove green, you have an odd size set.
Thank you very much. Somebody is requesting the PDF link. It will be sent to your email. The presentation and the questions will be sent to your email. Maybe
But I can send it if I'm allowed to on the chat as well.
Yeah, of course.
Okay.
So since we are almost out of time, I have two more questions. These are very general questions. I hope you answer them. So what are some good books for Olympiad combinatorics that you recommend?
Oh, that's an important question. Let me try to find. So let us cover this reasoning for a moment. It's recorded, so it won't disappear. So the books I would definitely recommend in combinatorics is a book by Mr. Angel, Problem Solving Strategies. It has several chapters about combinatorics, and that's a book in which you can find many of the problems that I presented to you as well. Another book on combinatorics, it's more, I think, academically oriented than Olympic oriented, but it also contains lots of problems in combinatorics to solve. It's by Łukasz Bożyk. It's a walk through combinatorics. And what more can I suggest? Of course, there are books with solutions and problems from different Olympiads around the world. So, for example, I know that at the Art of Problem Solving community, there are many problems there. And it's a forum like maintained by users from around the world, so there are plenty of problems there. But a book that would allow to learn combinatorics, the Olympic combinatorics. Just please give me a half more minute. I will try to find something that I could have, something else that I could recommend. Yeah, but the two present on the screen already are like enough material for long days and hours of combinatorial reading. So I hope they are somewhat enough. Yes, I don't think there is one that is general Olympic combinatorics. Radovan Putnam and beyond. I think they do have Olympic combinatorics, but it's oriented, I guess, towards academic competitions. So you will find there some analysis and linear algebra. Just forget about it and focus on combinatorics.
Thank you very much. So this will be the last question for today. What is the best way to tackle combinatorial questions? What advice would you give to beginners?
Best way to tackle combinatorial, I mean, it depends on what combinatorics it is about. I mean, combinatorics is hard. I tried to say a sentence about it at the beginning of our meeting, that in geometry you have all those theorems, all these facts, and all those lemmas that you can just take and try to use in a configuration. Similarly, in algebra, there are lots of inequalities and some crazy equations like number theory, mixed theory, and combinatorics. Well, you need to to understand what the problem is about, understand the structure behind it. It's handy to have, for example, some graph theoretical tools. So to represent the situation from the problem by some picture with dots and lines. Some parity or modular preparation from number theory, which leads to combinatorial proofs. And what I think that the best way to start this tackling combinatorial problems more and more is to see many problem techniques, because that's probably the thing that combinatorics has, like induction, I don't know, pigeonhole. Let's take an extremal element with respect to some property and focus on it, right? There's bijections similar to the ones I presented to you. So this understanding of how do things match with one another. I know that this is rough, but like combinatorics is everything that is not geometry, algebra, or number theory. So yeah, it's hard to find a common denominator for all this stuff. But what I recommend is to have a look at just proving stuff problems and see how the proofs are done. Like the indirect proof is a technique that you need to understand well in order to use it instantly in some parts of solving problems. So that's, I don't know how helpful it was, but that's what I think about combinatorics.
It was really helpful. Yeah, there was some very good advice. So that concludes our session today. That is the end of the questions and answers session. I thank you again for helping us and supporting us and taking this session for us and sharing whatever you felt was important to be shared to us. I hope you will be in touch with us and help more students here, and we will also try to get them in touch with you. Thank you very much, and I guess this is the end of the session.
Thank you very much as well. It was a pleasure to be here. I'm waiting for the contact from both students and looking forward to our contact.
Thank you very much.